Thank you very much for giving me the opportunity to discuss this, for me, rather new topic.
There's something wrong with the mic.
It's not on. Let's see, there's a... How about this?
Let me hear you.
You hear me? Do you hear me now? Do you hear me now?
Yeah, push that. Okay. Okay, I can hear myself now. That's even better. All right. So as I said, this is for me a rather new topic that I've started to venture into in collaboration with a number of people. You see listed here, Van der Watman, a PhD student at CWI, who is co-supervised by me and by Jason Frank, also here in the audience. Another grad student who just started, Debrati Baumik, and another CWI colleague, Bert Zwart. So this all started at CWI, and Jason, of course, just moved to Utrecht University. Okay, a brief outline. I'll say something very briefly about Monte Carlo simulation and rare events. What is the problem if you do straightforward? Can you hear me? Yeah. Okay. I'll speak louder. Then I'll say something about splitting. So what is splitting? Multi-level splitting, and how can it help you to simulate rare events more efficiently? Next, I'll move on to steady-state simulation. How can the splitting technique help you to estimate probabilities of steady-state probabilities of distributions? And then in the end, I'll give an example about reliability of power grids, which is the topic how I and the people I just mentioned sort of got into this field. Of course, it's not a climate example. I'd hoped to have finished an example on that in time, but that didn't happen. So I'll show this example instead. Okay. So this is sort of a very brief version of how you can use Monte Carlo simulation to estimate rare events. Suppose you have a random variable and you take a number of samples from that, and you want to estimate the probability that the random variable is in some set A. Then, of course, the most straightforward thing to do is to use this estimator where you just count the number of samples that fall in this set. You divide by the total number of samples, and that gives you the estimator. Right? That would be sort of the straightforward, and in the context of rare events, I see it often referred to as crude or naive Monte Carlo simulation. Now, the problem with that is that the relative error of this estimator blows up as the probability approaches zero. So as I've written here, if the probability is small enough, so for gamma much smaller than 1, the squared relative error scales in this way, so 1 over the number of samples times the rare event probability. And that means that if you have some desired accuracy of your estimator, so you want to fix this squared relative error at some value, then it means that the number of samples can go up enormously if you have a very small probability that you try to estimate. Right? And that can, if gamma is truly small, that can become a computational barrier to coming up with good estimates. Now this problem has been known from the early days of Monte Carlo simulation, and people have already a long time ago, and in fact this also came out of the first era of the MC method. People have thought of ways to do this more efficiently, and there are two sort of major categories of techniques that have been proposed already decades ago. So one is importance sampling, and the idea there is to use a change of measure for the random variable so that the rare event becomes less rare, essentially. Okay, now the finding the good change of measure can be very difficult, and that's one of the big challenges of importance sampling. I understand. I'm not going to say more about that. I've not used it or really tried it for the examples that we worked on, but it is sort of a big category of techniques to come up with more efficient Monte Carlo methods. Now, the other category that I want to talk about here is called splitting, and the idea there is to use a sequence of embedded subsets. So the set we're interested in the end is the rare event set is A, and we use a sequence of subsets where each next one is embedded into the previous one, and then the probability of finding the random variable in the rare event set becomes a product of conditional probabilities. Right? These probabilities here. What is the probability of finding X sort of in the next level subset, given that it is in the previous level subset? Right? And then the idea is that all these factors in this product are not small, so that will become much easier to estimate. Okay, so here's an example. Suppose you have a stochastic process and you want to estimate the probability that it hits, right? It starts at 0 and you want to estimate the probability that it hits the rare event set within a given time interval, right? So that's what I've expressed here. So what is the probability that the first time that it hits this set A, that it's smaller than some given time capital T? Okay, now we define sort of these for these intermediate these subsets. We define these tau sub k. So that's sort of the first hitting time for these subsets, right? So and again, instead of trying to estimate this quantity directly, you can try to estimate all these conditional probabilities separately for all the k. Let's say here. So in this context, it's given that your process has hit a certain level, what is the probability that's going to hit the next level as well? Right? Then you can do that subsequently and form the product, and by that way estimate the rare event probability. Now the idea of splitting is to do that by launching trajectories that you split into replicas, into copies, each time they hit sort of the next subset. So this is a very schematic example. So xt here on the vertical starts at 0, and there the level that we're interested in ultimately is given by this straight red line. So what's the probability that it's going to cross this mu3 within a given time? So you can define these intermediate levels. These are the dashed lines, and every time the path crosses this level, you split it into a number of copies, which are then also propagated in time. And again, if they do not cross the next level, then you just continue till the end. If they do hit the next level, then they're split into multiple copies, which are also propagated forward in time. Right, so let's say we have n sub k paths that start from a given level, from the n sub k entrance states for the set A sub k, and then assume that rk of these reach the next level before time is up, essentially before the capital T. Then the estimator for these conditional probabilities, so this p hat k, is just the quotient of these, right? So you just divide the number of hits at the next level by the number of total trajectories that was launched at the previous level, and that's an estimator for this conditional probability. And you need to do that at every level, and then the product is then an estimator for the rare event probability. And an important aspect is that this estimator is an unbiased estimator for the rare event probability. does not hold true for these p-hat case. These are not guaranteed to be unbiased estimators of these separate conditional probabilities, but the product is in fact unbiased. Okay, now this, as I already said, this the idea of splitting is fairly old. The earliest references go back to this paper here, Kahn and Harris, from 1951. So it has a long history and has been used in several fields. Queuing theory, queuing systems, and communication networks. There's a lot of literature there that makes use of these techniques. It's used for reliability analysis, where some people have dubbed this stochastic subset simulation. It's also used in computational chemistry, but I think, as far as I know, it is hardly being used in the context of climate science, which is quite interesting, I think, to study this and see if this is a useful technique for studying extremes in geophysical systems. Yeah, so a bunch of references. There's a sort of a class of methods in this sort of splitting class called restart that's been quite popular. There, one of the aspects is that when a trajectory sort of goes too much down, it crosses the next level downwards, then it's terminated. Right? This sort of increases the computational efficiency in principle. So, as I mentioned, a lot of literature in relating to queuing theory. For instance, there's a paper by Glasman et al. On operations research, a thesis by Garvels, where a lot of these things are written up in much detail. An overview book on rare event simulation with one chapter by Lecuyer et al. On splitting. And then, as I mentioned, computational chemistry, this is a set of techniques that evolved somewhat independently from the more queuing theory related work. There's a review paper by Allen et al. From a few years ago.
Needs to speak louder.
Oh, I'm sorry. I hope the mic is doing its work. Anyway, it goes by several names. For it, flux sampling is one of them. There are several variants there, and I think Eric van den Eijden, all the way in the back, knows a lot about these techniques as they're used in chemistry. Okay, so far there's a lot more literature, but I'll leave it at this. I want to give you a few numerical examples. So here is the Ornstein-Uhlenbeck process. Of course, what do you start with if you want to try this out and see how it works? You start with the Ornstein-Uhlenbeck process. What I did is try to estimate the probability of the process crossing 5 times the standard deviation on the positive side from the mean within a fixed time interval. In this case, it's between 0 and 1. So I started at 0. I want to know what is the probability that it hits 5 times standard deviation within this time interval. Okay, now if you do this with this crude Monte Carlo method, if you want to do it computationally, of course, for Ornstein-Uhlenbeck process, there are a lot of things you can do by hand. But if you want to do it with the sort of straightforward Monte Carlo method, to reach this probability with a relative error, that's I think for all kinds of purposes acceptable. I needed 100 million Monte Carlo samples, and it took me to repeat this a number of times so that I can compute the relative error. It took 60 hours, so quite a long time. And this is just on a sort of simple implementation on a workstation. So surely it can be done faster, but the main point is that if you do the splitting, the computation time goes down dramatically to reach a similar relative error and indeed a similar answer. Using 10 levels with the splitting methods, that took me about 10 minutes. So you see that the computational gain is enormous in this case, which was of course the whole point of using this method. Okay, now there are several things that you have to consider if you want to use this, and one main question is, how do you choose the number of copies for each sample, for each path that hits a certain subset level? So there are several variants there. The most straightforward thing, I think, is this fixed splitting. Every path that hits a given level is split into a fixed number of copies. Right. So if you have R sub k entrance states into a certain subset, then you split each of them in the same number of copies. So this is the way this sort of number of new paths to go to the next level is fixed. Okay. Now another variant is fixed effort, where the total number, this n sub k, is fixed on beforehand. And then you sample either completely randomly or in some stratified way from the entrance states that you do have. And that means that you have control of the computational effort. Right? You know how much time it's going to take to complete the entire calculation. But it doesn't give you any guarantee on the accuracy of the estimator. Now, the very recent variant that was proposed a few years ago in this paper that I mentioned here goes by the name of fixed number of successes, and there the idea is not to fix on beforehand the number of copies that you launch at each level, but to fix the number of successes. So the number of successful paths that start and that hit the next level. So rather than fixing n, you fix r. And you sample from the entrance states until you've reached the desired number of successes. So hence the name fixed number of successes. And that gives you control over the estimator accuracy. But of course, the downside is that it does not give you control over the computational effort. So it may take, in a way, this algorithm sort of adjusts the computational effort so that it will give you the estimator accuracy that you want. Okay, now the example that I showed just before from the Orton-Ullbeck process was in some sense about a transient probability. You start at a state, what is the probability of hitting some rare event set within a given time. But of course, for all kinds of purposes, it would be interesting to say something about the till of an invariant probability distribution. What is the probability, right, the steady state probability of being in a rare event set with your stochastic process? Right, so how do you estimate this kind of steady state probability? For that purpose as well, you can use this splitting method in the following way. Let's say we have this the rare event set given by all those states where some function of x, which is called the importance function, is above some threshold, right, in this way. Now, if you can assume, and of course this is not a non-trivial assumption, if you can assume that the process that you get out of, right, this mapping of xt, this function of xt, if you can assume that is a regenerative process, then you can use the main theorem for regenerative processes, and that says that the probability that you're interested in can be written as a fraction of the expected time spent in the rare event set during a cycle, or a regenerative cycle, divided by the expected length of the regenerative cycle. Right, so a regenerative process is a process.
Really, with your dropping your voice from time to time, I really would like to hear the definition of regenerative.
Well, yeah, it's only written down very, very shorthandedly. The idea is that the regenerative process can be decomposed or split into IID cycles, so that all the properties of the process during a cycle are independent of what happens during previous cycles. So,
the cycle is random.
Excuse me?
The length of the
Yes.
cycle is random.
Yeah, absolutely. Yeah. But they're random, but so the length is also IID. That's crucial. Yeah. And if that holds true, right, then we can use this fraction to estimate the probability, and so the expectation of the time spent in a rare event set can then be decomposed in this way. The law of iterated functions, iterated expectations, where you basically write the expectation of the time spent in a rare event set as the probability that you will hit the rare event set multiplied by the expected time in the rare event set given that you have hit it, right? Which is this expectation here. Now this probability, as I wrote here, that is the one that you can estimate by splitting because that's the rare event probability. That's the one that's going to take a lot of computational time if this is indeed a rare event probability. And then the other expectations are straightforward. So the expectation for the length of the regenerative cycle can just be computed by launching a number of cycles, and no matter how long or how short they are, you just use them, and that will give you an estimate of the mean of the cycle length. And the same for this one here. You can launch a number of trajectories at the entrance of the rare event sets and just follow them and see how long they stay in the rare event set, and it will give you an easy estimation of this expectation. So again, the Ornstein-Unruh process. Here I computed the probability that the process is beyond 5 standard deviations from the mean, from 0 in this case, using this whole setup. So in a straightforward way, somehow this thing got stuck. Oh, okay. Just by very long integration. And this is one thing you can do. Take the process, just integrate it for an awfully long time, and just count or keep book of how much time it spends in the rare event set. And of course, the rarer the events, the longer the simulation that you need. So this can come down to extremely long integrations in order to come up with an estimate that has a reasonable, acceptable relative error. So in this particular case, this took me about 10,000 seconds to do this. With the splitting, using, in this case, 12 levels, it took me about 500 seconds. And the regenerative cycle in this case was defined starting at 0, and the process has to cross 1 and go back to 0, and that sort of determines the cycle. Of course, it's again, the length is random. And so here again, it's a big speed up for this steady state probability compared to the naive Monte Carlo method. And of course, the interesting thing about these kinds of techniques is that so the computational gain increases the smaller the probability that you try to compute. I'd expect the computational gain, if I wanted to know what is the probability of being beyond 6 or 7 standard deviations, the computational gain is going to be even more than it is here. Okay. Now, as I said, the way that I got into this topic with Wander Watman and Jason Frank is because we're interested in estimating the reliability of power grids. So electricity grids with renewable energy sources, for instance, from wind farms or solar panels. And there, of course, an obvious question is, well, if you have these kinds of energy sources and they're intermittent and unpredictable, what is the probability that you get a grid failure, right? Because by some improbable but not completely impossible combination of circumstances of generation on one side of the grid and consumption on the other side of the grid, you may overload the network one way or another. So what is the probability that this happens? That's the backdrop for this study. And the idea is to model the power source, and if you want the power consumption, but we've limited ourselves so far to the power source, model power sources as stochastic processes. And then what needs to be done is that for every time, so you evolve these stochastic power sources in time, and at every time step you have to solve what are called power flow equations, which are equations that will give you the voltages and the currents in the network given all the power input and output at various nodes and the network topology. So what are the actual connections between the nodes and what is the resistance of the cables between them. This is what you have to put in there. And this comes down to solving a couple set of nonlinear equations, algebraic equations, at every time step. So it's time consuming if you want to do this for for a long period of time, and at every time step you have to repeat this. It's computationally quite expensive. So what is failure in this context? For us, we chose this to be the case where one or several of the constraints on the voltages and the currents in the network is not satisfied. Right, so obviously the cables in the network can only carry a maximum amount of currents before they start to be overloaded. So these are the constraints that you have to stay within, and the question is, what is the probability that you're going beyond this? So we have a very simple network consisting of 3 nodes where there is a stochastic power source, so a wind farm, but we modeled it as an Ornstein-Uhlenbeck process. There's consumption, which is constant in we've kept that constant so far, and then another is what's called a slack bus in the network. So let me not explain much more about this. So the Ornstein-Uhlenbeck process determines the power inputs. We evolve it in time, and we want to compute the failure probability. Now, in this case, the failure probability, right? So the probability that a grid operator, if there were one for the simple grid, would have to, for instance, cut power for this little house here, because otherwise the network would be overloaded. The probability of that is small, with all the settings that we chose, which are detailed in the paper. And in this case, we used the steady state simulation with splitting, and that in this case gave us about a 80-fold efficiency gain compared to the Kroon Monte Carlo. Again, so this is definitely less trivial example than the Ornstein-Uhlenbeck process, but you can see that this is again a feasible method for this purpose. Okay, I thought I had the reference for the paper here, but I think I showed it before. So let me go to the conclusions. So I hope I've been able to convey that splitting, multi-level splitting, can give large efficiency gains if you want to estimate rare event probabilities. This particular variant that we use, or the examples that I showed, all made use of this fixed number of successes variant. It gives you control over the accuracy, but as I mentioned, no control over the computational effort. It can be used for estimating steady state probabilities, even though sort of the principal idea is really targeted at transient probabilities. And there's several, of course, difficult things to consider always when using this. So one of them is for the steady state probabilities, that the assumption of the regenerative properties is non-trivial, for sure. And somewhat related to that, finding a good importance function can be difficult, right? So essentially that's the function. If you choose it in the right way, you can assume the regenerative property, but not always, right? So this is a crucial point in making this splitting method work well. Choose a good importance function. So that's a challenge, and how that will work out in more geophysically oriented examples is it's something to look into, and I hope I will be able to tell you a little more about that at the next meeting. So thank you.
Thank you also for being perfect in time.
Well, we are working on the same problem for 2 years with Eric Simonet, having in mind also application in geophysics.
Okay.
And, for instance, currently we are able to compute rare transition in the Ginzburg-Landau equation. And
So you use splitting or importance sampling for that?
we use splitting. Actually, we use something which is called adaptative multi-level splitting, which in a sense answers your last question, because then the levels are chosen adaptatively, such that you don't need really to fix a priori the importance function.
You don't need to fix the importance function. Okay. Well, so this is something I didn't discuss. The choice of the thresholds. So this is something you can also, which I in fact did, do adaptively, because if you fix that one beforehand, then it can be that between two levels, the probability of switching from one to next can somehow be very small. So you want to sort of increase the number of thresholds in that region, and maybe decrease in other regions. So I'm not sure if this is also part of your adaptive strategy.
It's not our strategy. It has been developed before by some people in France.
Okay.
I can give you the reference.
Oh yeah, I'd love to hear. That's great.
Also, a reference, I think, there's some nice work recently. There's indeed a lot of work on splitting, but some recent work also by Henry Kunsch, a colleague at ETH, who makes very nice links with particle filters and Kalman filtering.
Okay, so this is
all
all the work by.
with the school in France also. I think you might be interested to see.
So this is the same Kunsch as the from Amrein and Kunsch, because I showed the reference.
Oh, so I'm writing Kunsch, yeah.
Yeah. It's
But there's also, I think, some new work with the student Frey, F-R-E-I.
okay. All right.
Nice
Great.
work.
Thanks. Yeah.
Can I just check that I understood what you said when you were talking about the regenerative property, that you were talking about the difference between the ratio of the time above the threshold to the time between each beginning of the regenerative process, and you're relating that to the complementary CDF, the 1 minus the CDF, probability of being above the threshold.
Yeah, so you mean the fraction, so you compute the expected time during one regenerative cycle, the expected time above the threshold.
And that was related to the CDF on the other side.
Yeah.
Yeah, okay. That property, I mean, it's been used in engineering, for example, by people like Van Mark, as an approximation. I'm interested that you're using it as in the context of this regenerative property. Is it a consequence of the regenerative property, or is it, which leads to which?
I mean that you can use this
relationship. Is that a consequence in your mind of the regenerative property, and how tight are the assumptions on?
Yeah, I think this is the main property of regenerative processes, that you can write it in this way.
Okay, and how constrained are systems? I mean, what sort of systems would you a priori expect that to fail for?
It's difficult to say. It's
the reason I ask is I've been trying to simulate it on various things, and it seems to behave a lot better than it should. That's why I'm curious is what obviously breaks it.
Well, you can imagine that if you, I think it's non-trivial. If you take up, for instance, a projection, you have a stochastic process in more than one dimension. You project it into some, say, one-dimensional function.
Yeah.
The way you do that, I guess it's a little bit comparable to the question whether or not you retain the Markov property.
Okay.
Again, for Markov property, it's more difficult, because if you have a regenerative process and you take a function of that, then that function is also going to be regenerative.
Okay.
But it's not obvious that, in particular, if you think of projections, the way you do that can really make a difference whether or not there's some kind of memory of the previous cycles.
Yeah, well,
that influences the next cycle.
I've been surprised how robust it is on the few things I've tried.
Okay, well, that's encouraging to hear.
Any other question? Well, if not, thank you again.